Hey, everybody. Great to be here. This is actually my second time at the NLP Summit. And this time I'm going to talk about something that's very interesting to me, near and dear to my heart. We're going to talk a little bit about how you can use large language models, vector databases, retrieval to build a super doctor. And so my name is Zain. I'm a senior developer advocate at Weaviate. Um, let's dive right into it. So if you think about the average human doctor, they study for 7+ years after their undergrad, so 4 years of undergrad and then 7+ years, and this can increase depending on what specialty they go into. And on average, they see about 100,000 patients in their entire lifetime. So this is you can think of this as their training data for the incremental patient that they're seeing. Their performance depends on how many patients they've seen and how much they've studied. So my question was, could we build an AI powered medical doctor or an assistant? Um, and so some of the qualifications for this would have to be that it needs to have access to more data than any human doctor, right? Because it's AI powered, because it has the ability to retrieve information from a knowledge base, it can now retrieve from more information than any human can possibly have. Right? It needs to be able to search for relevant information. There is a sea of data out there. It needs to determine which other patients and which other articles are related to the current patient that it's trying to diagnose or assist. It also needs to be explainable. Right? It can't just diagnose without explainability. It needs to give reasons. It needs to cite sources as to I am giving this diagnosis because of patient X, Y, and Z that I've seen in the past. Um, and it also needs to reason over technical medical concepts. So it needs to understand uh, on the level that a doctor understands as well. And to wrap this whole thing together, it needs to do this in real time. So it can't go away for a week and then come back and tell you what the diagnosis is. In order for it to be a useful assistant, it has to do this in real time. And so another kind of plus point of this presentation is that every technology that I use in this presentation, uh, is actually open source. So you can reproduce this uh, super doctor from beginning to end if you wanted using open source technology. So let's dive into it. So the simplest approach you could have is you take the patient's information and you give it to a language model, and the language model generates diagnoses, right? So this is a direct prompting where you you give it the task to diagnose a patient, and it goes about and does that, right? If the large language model in this case under consideration is fine-tuned on biomedical data, you can see probably a performance increase because now it's been kind of fine-tuned in the domain that we needed to perform in. Right? And if the user knows how to prompt the language model correctly, you'll also see a boost in performance. So if, for example, the user gives the language model examples or asks it to do chain of thought, you'll get better improvements here as well. Right? But this is the simplest approach that you could take to make this super doctor. Right? So let's see how we can build on top of this. How can we improve on this? Right? An improved approach, which I call the RAG doctor, the retrieval augmented generation doctor, is one where you've got all of your medical information, and then you take the current patient's information and you see what is the relevant information that should be read for this particular patient. So you extract that out, and then you take your patient information and the extracted information, you give that to your language model, and you ask it to output diagnoses, reason over this information. Right? And so here you need to be able to search for similar patients and publications and cases. You need to be able to pass the relevant information to a language model, and then the language model performs this retrieve then read operation. Right? And this allows you to cite sources because you know exactly which documents you retrieved from your knowledge base. And so that can be cited when the language model makes its proposal diagnoses, right? So it is explainable in a way. So what I want to do is deconstruct each one of these step by step. Right? So where do these come from? This is actually an open source data set called the PMC patients data set, which you can get at this link at the bottom. This has about 170,000 patient case summaries that they've extracted from PubMed articles. And to boot, it also has about 1.4 million PubMed articles, abstracts that you can use to extract knowledge from as well. Right? And so this is all part of a benchmark for information retrieval, and uh, it's made with this idea of retrieving similar patients and articles in mind. So you can use both of these frameworks to understand, given this new patient's information, what other patients are similar and what other articles are similar to this new patient. So that's our data set covered. Right? The next idea here is we need a way to search over this data. We have about 1.4 million articles and 200,000 patient cases. We need a way to extract out the two most similar patient cases and the two most similar articles. And that's where the vector database comes in. Right? So a vector database essentially allows you to store billions of documents and articles and patient cases and retrieve the most similar ones in real time. So you're going to give this vector database a query of these are the patient, this is the patient, and this is their kind of symptoms and ailment, and it's going to go into your database and retrieve for you the most similar patients and the most similar articles. And so here we use the open source vector database called Weaviate. You can have a look at this. It's really easy to get started with. But essentially how this works is given a query, so here it could be my left shoulder hurts and I have numbness in my thumb and index finger. This could be what a patient comes to you with. You put that into the vector database, and we'll talk about how that happens in a second. But outcome, once this is put into the database, you retrieve the most related patients. So here, ID 43163 and 9122 are the most related to this new patient that you're seeing, and the most related articles. And so this is what a vector database does. It performs vector search over your millions of documents, and it says these are the most relevant ones. So how does the actual vector database work? Well, first of all, you have to take all of your patient cases that are here and you need to embed them into vectors. So they need to be represented in this vector format. So you need a model that understands the medical domain to be able to embed all this data into vectors. So there's an open source model called MedCPT Query Encoder. This can actually take patient level information and it can encode it into a vector. So it's almost a numerical representation for what the patient has to say about their current ailment. And then there's also a separate open source model called MedCPT Article Encoder, and this one takes into account longer form documents like abstracts and papers and patient summaries, and it embeds these into vector space. And so if you use this type of model, you can actually embed your patient information and your documents into the same vector space, and then you can retrieve the most similar patients, similar to what I talked about in the last slide. Right? And so this is also open source. You can read the paper and get the code down there at the link. Right? And then, like I mentioned before, it does help if your language model is fine-tuned on the medical space. So here, what you can choose to use is the class of models called the Meditron models. So these Meditron models are open source, and these have been pre-trained and fine-tuned on billions of tokens. So they've been pre-trained on around 50 billion medical domain tokens, and they've also been supervised fine-tuned on medical domain tasks as well. Right? And so these outperform general purpose models like Llama 2, 70 billion, and GPT 3.5 on medical tasks. And so there's a rich kind of pipeline of pre-training and supervised fine-tuning that went into Meditron, and you can take advantage of this as well. Okay, so that's the first part, right? We've got our RAG doctor set up. Um, the next part of this talk is how can we do even better? Right? Can we make this system better than it is right now? Right? And so this is where I want to introduce some advanced retrieval augmented generation techniques that are going to help us increase the reliability of this system. The first thing that we're going to do is rewrite our queries. And so the idea here is, we don't really know how best to frame our queries to a language model. We don't really know how best to pose the information about this particular patient to a vector database, nor do we know how to write the best prompt such that a language model can understand exactly what we want to do and give us the best answer. So what we want to do is write an initial query, and then we want to rewrite it into its best format. Right? So we want to rewrite both the query that goes to the vector database and the one that goes to the large language model. And there's open source frameworks that allow us to do this. Right? We've got open source frameworks like DSPY that rewrite the query to the language model. And we've also got open source frameworks and academic work on this from this paper called Query Rewriting that rewrites the query that goes to the vector database for you. Right? So let's see how this works in action. Imagine your uh, patient comes to you and asks you this same query, right? My left shoulder hurts and I have numbness in my thumb and index finger. You can take this input, pass it over to a language model, and you can get it to rewrite this in a format that uh, best captures the essence of what's being conveyed and gives you the correct output most of the times. So maybe this language model, this black box rewriter, rewrites this query in this format. So now it writes pain left shoulder, numbness thumb, numbness index finger. This is a lot less interpretable to humans, but that's the point. It's a lot more interpretable to the vector database. Right? And so now you use this query going forward. We also want to rewrite our query for the language model. Right? So if we go to the language model and we say, I have this patient, uh, this is what their problems are, and these are similar patients and articles that I've retrieved. Have a read over these and tell me what a potential diagnosis for this patient could be. That might not be the best way to prompt a language model to solve this problem for us. So we can use a framework like DSPY that does this prompt rewriting and optimal prompt generation to give us the best prompt for a given scenario. And so here we can rewrite both the query and the prompt to the language model. Another type of optimization that we can do here is introducing hybrid search. And so this has to do with improving the vector database and how many relevant results you can get back from the vector database. And so the main idea here is that medicine as a domain has a lot of very specific keywords that you might want to search on, right? If a patient is on a very particular type of medicine, or they have a very particular type of symptom, or they have pain at a very at a particular anatomy, those are keywords that you might want to match your reference patient cases and your reference articles for. So the problem is that with vector search, the way that I described it earlier, where you've got embeddings for these patients and articles, this does not really match too well on keywords. It matches really great on semantic similarity, understanding the meaning behind it, but it doesn't actually match very well on word or text pairings. Right? For that, we have keyword search, right? So there's these two streams of search technologies that you can use, vector search and more classical keyword search, that are good. They both have their pros and cons. What we'd like to do is have the best of both worlds. And so to do that, you get hybrid search. Hybrid search is a hybrid of both vector and keyword search, and it uses both of these to improve the relevance of the articles that are retrieved from here and then eventually go to the large language model. And so here we now take advantage of both vector search and keyword search to improve the results that come out from the vector database. And this is actually implemented out of the box in Weaviate. And so you think, okay, this is some very difficult type of optimization that needs to happen. But in fact, if you look at the code change, it's literally one word of code change that takes you from pure vector search to now a hybrid search approach. So it's very easy to implement this. And this is probably in production what will give you the biggest improvement in performance. And in production, a lot of customers use this. All right. So the next optimization that we can make here is called AutoCut. So AutoCut has to do with filtering what's returned and then seeing whether it's relevant. So the idea here is if you see everything that comes back from your database and you realize that some of these things are irrelevant, you automatically just cut them off and they never go to the language model so that it can read this irrelevant stuff. Right? And so here, the vector database looks at what's returned and it measures the similarity of those objects. And anytime there's a class of objects that are very far away from similar objects, i.e., they're dissimilar, so there's a big jump in similarity, it'll just cut off the irrelevant objects. Right? And so this helps because now the language model doesn't have to read over useless information. You've essentially nipped the problem in the bud and you've removed those results rather than passing it over to a language model. And this, again, you could think is pretty difficult to quantify. How would you actually do this? Let's have a look at an example, right? Let's say you come in with your rewritten query here. You go in and your vector database now this time gives you these 6 patient cases that are the most similar, right? And we're actually going to dive a little bit deeper. We now also get information about how similar this patient's case is to this particular query. So this has a similarity score of 32, right? And you can see that this one is quite similar, 30, 27, 26, and then you get a big jump from 26 to 7. That means that these two cases are a lot less similar than all of these previous 4 cases. So what AutoCut is going to do is essentially just say, there's a big jump. These 2 cases are probably irrelevant. We're going to cut that off and we're not going to return that to the user. And so this makes sure that if you've got some irrelevant results right at the end of a bunch of relevant results, they never pass the test and they get dropped. Right? And so to implement this in Weaviate, the vector database, this is actually also just one line of code. You can tell it how many groups to keep. And so here we chose to keep one group of patient cases that are similar, and everything else will get discarded, and irrelevant results won't be sent to the language model so that it can get confused. Okay. And then the last thing that we'll do to optimize this is called re-ranking. So what this does is look at all of these filtered results that have come through the hybrid search approach, the auto cut approach, the query rewritten approach. Now these are really, really good, relevant articles. What we're going to do now is do a last check on how relevant these are. So the main idea is we want the model to sift through everything that this database thinks is relevant to this particular patient's information, and we ask a separate model to re-rank them, right? Just so we have one last kind of pass through these documents. And so we want to over retrieve, and maybe before we were retrieving 5 documents, now we want to retrieve 25 documents. We retrieve a lot more. And then we have a very heavy and powerful model look at all 25 of these documents in excruciating detail. And we get it to re-rank them from the most relevant to the least relevant. And then we select out the ones that are important and relevant, and we give that over to a language model. And this significantly improves the quality of the cases that are relevant to this patient that the language model now sees and reasons over. And so if we think about how this is actually carried out, you start off as you would with your query. This is information of a patient that goes into your vector database. And now you get out a bunch of results. Now we've over retrieved, we've over sampled, and now we get out a lot of patient cases that are relevant to this query. And so we've got a similarity score for every single patient case over here as well. What we're now going to do is, rather than use these similarity scores right out of the box, we're going to pass this over to a re-ranker model, and we're going to ask it to redo these rankings based on how it thinks these patient cases are similar or dissimilar to the patient case that we passed in the query. Right? And so it goes in and it does its job of re-ranking, and maybe it decides that this first patient case is actually not that similar. It deserves a third place spot. The third place spot actually deserves a first spot, and this guy here deserves the second place spot, right? So it goes in and it re-ranks and shuffles the ranking based on what it thinks is the most similar to the query. And now you get another set of scores here. And now you can go ahead and choose, okay, from these re-ranked results, I want to pick the top 5 or top 6 most relevant patient cases, and I can send those over to a language model to read and then make the diagnosis for this or make the suggestion for this new patient that I'm seeing for the first time. And so this again seems like a very complicated and detailed process. But again, this is a few lines of code implemented in the vector database. So actually, this is one line of code that can be expanded onto a multi-line of code where you do your query, and as a part of your query, you can pass in a variable called re-rank, and you ask it to re-rank based on a particular property that you're passing in, and you pass in a new query that it can use to re-rank your results with respect to. And the power here is that this new model is trained specifically to re-rank, and it's a lot heavier and more powerful. Okay, so that essentially brings our RAG doctor plus all of these incremental improvements that we've made with query rewriting, with hybrid search, with the other improvements, now to a point where This will suggest really good diagnoses that a doctor can now look over, sift over, and use this to inform that patient's care. Right? So here it retrieves from a knowledge base that is larger than any human can. It proposes plausible diagnosis, and it can also source citations. It can say, based on these patients that you've seen in the past, this is what this new patient should be diagnosed with. Right? And it can reason over the previous patterns of patients as well as published articles as well. And to boot, it does this all in real time. It does this in a few seconds end to end. So a patient comes in, you pass in the information for that patient. It does this retrieval, read, rewriting, hybrid search, everything that we've talked about in real time in under a second, and you get potential diagnoses for the new patient. And so if you guys are interested in this, um, check out the technology. I'll also send these slides, but I'm also here to answer any questions. If you do have questions later on, feel free to connect with me. I'm always happy to carry the conversation forward. Thanks, everybody. Hope you found this useful, and you hope you enjoyed it.